Hello, welcome. The new week. I hope the exam one went well. Yes, you can give me a small signal that you can hear me. Unless you're doing something and I don't see. Oh yeah, I see Thomas, I see Aravinda. Okay. Rishabh. Okay, I see a couple of reactions. Good. Okay. Yeah, if you're using the chat box, you definitely can send the message to everyone. Yes, not like don't send the direct message because then only me or only other students can see. Okay, that means first of all, I don't know what was the average. I can check probably somewhere, but we're not really looking, and the average. Average is a not really good indicator what's going on, because even if the average is like 70% or 80%, not everybody get that number. Yeah, that means the average, it's not different, different statistic like parameters could be helpful, but the mean, the average is not helpful. And even let's say you earn 60% and somebody and the average is like 90. What this means? That you did extremely poor? Not necessary, because depends on the situation, depends. Or maybe the other way, like you achieve 90% and the average is 60, for instance. Yes, I don't know. That's when average is a not good indicator to compare. And we don't usually curve the tests in mathematics. You probably know this. Okay, in general, I still didn't check the average, and I will not, but I saw the numbers and I saw lots of 100%, I saw lots of 90% or above 90, which this makes me really, really happy. Yeah, it is possible to get the highest number on the test if you work hard, if you work every day. Yes, consistency is the key. We remember that, and and if you follow all of the instructions, the practice, I mean, not the practice, the sample, the practice problems that we provide for you to prepare for the test. If you solved all of them, if you feel confident, you definitely achieve a good number, you earn a good number. And now we're starting another sequence. Actually, today we will cover sequences, but we're starting another sequence of 3 weeks. Also, focus, every day counts, every minute counts, and then we will take the second midterm. Okay, that's the plan. Yes, the extra credit, I will, later today, I will update the extra credit, for the practice test, 5 points. Everybody will get 5 points who took the practice test out of 0. That means this will be extra. And also, I will update, but I will send the announcement. I will update the Achieve score. Achieve the online homework on the Achieve platform, the total number of points for the semester is 100, but I can maybe consider that we are almost halfway through. That means I will type 50 points, because if I will put 100, then it will be not good for the rest of your grades. I will put 50 points, and then I will transfer the percentage that you earn on the Achieve. That means whatever percentage will be sitting in your gradebook on the Achieve tonight, like this evening, because as soon as you complete more and more, the percentage can change. That means, let's say if you're changing even now, or after the session, let's say you have 92%, then I will put 92% on the Canvas gradebook. Okay, that means I will transfer this percentage, and it will be based on the 50 points at the moment, just to balance all of the scores. But at the end of the semester, it will be out of 100 points. based on the syllabus. Okay, that's all of the announcement. In general, the feedback is that I'm thinking about the second midterm because we're starting, and I did start creating the second midterm. That's probably I'm saying. The feedback for the first midterm, I can say everything looks good. Yeah? I definitely see beautiful numbers, good numbers, high numbers, and I'm really, really happy about this. Yeah? I know that my students are working, and yes, I have the best students in the classroom. That's me. Thank you for your hard work and yes, the dedication to the course, to your actually knowledge. Yeah? Okay. Okay, let's start. Aravinda, I don't know what you're asking for. What's that for? I don't know what is that. If you can ask again, I can possibly answer. Oh, the Achieve, yes, the online homework assignments. Yes, we do have online homework assignment. I hope all of the students are aware. Okay. That's me. Now let's start because we are starting chapter 10. And chapter 10 is, yeah, it's still calculus and we will still have lots of calculus, but it's a little bit different. We just, for a second, we will go away from the integration. Oh, we will come back sooner than we think, but we just start this infinite sequences and series. That means today I will introduce sequences, and yeah, let's start from there. Okay, let's see. Oh, my screen is not okay. That means first of all, we started, yes, ready, answer all of my questions, and I will try to answer yours. What do you think, like what sequences are? What is sequence? How do you understand this? Can somebody, you can write something, you can tell me, what is sequence? Yeah, I hope we understand. I'm not asking for mathematical description, mathematical definition. No, just sequence. Do we know what is sequence? A pattern, yes, we can say a pattern, or even easier, an order. Yes, it's like a sequence. It's the order, the series. Yes, the series is mathematically is different, but yeah, of related items. Yes, the order of something, a pattern, the order of, yes, something that is connected by a certain pattern. We can say this way. Or we may have an order of items without any like connection. That will be also a sequence. Chaotic one, but a sequence. Okay, that's me. Let's see what I typed. Okay, that's me. Let's look at my first slide. The sequence is, of course, the list of numbers written in a definite order. That's, we will always have an order. And how we will like label the terms. We will have A sub 1 will be the first term. A sub 2 will be a second term. A sub 3, A sub 4, and so on. That means we may notice that index, yes, n is called an index. It's the n, yeah, for all chapter 10. N will represent counting numbers. That means n belongs to, mathematically, we call natural numbers. And it's like counting numbers. Yeah, because we have the first term, second, third, fourth. That means we have numbers 1, 2, 3, 4, positive, and so on, positive integers. That means this is like a little bit of discrete mathematics. Yeah? We not, between 1 and 2, we have no inputs, no numbers. We just using the positive integer. That means n is a positive integer, counting numbers. And that means, and they changing by 1. Yes, because it's 1, 2, 3, 4, 5. That's how we count. That means this is like general term, A sub n. Yeah, A sub 1 and A sub 2, 3, 4, and 5. we have to be able to define a term before, like one before a sub n. It will be a sub n minus 1. And also after will be a term a sub n plus 1. And I can even keep going, a sub n plus 2, and so on. Right? That means that's also important. A sub n, but a sub n plus 1, and a sub n plus 2, and so on. Okay, that means that's the terms. And we definitely will deal with the infinite sequence. Yeah? If we have a sequence and we will realize the pattern, we always assume that the pattern continue forever. Okay? Okay. Now, what we can do? We may call a sequence as a function, but we will not really say like f of n, like we saying f of x. No, we will say we will still have this general notation a sub n. Yeah? We usually have this label, this notation a sub n, but we can say that the sequence is a function whose the inputs, the domain, are set of positive integers. Yeah? That means n, because when we will say f of x, we know usually that x is like, we have to know how to set up the domain, but usually it's like all of the numbers, yeah, all real numbers. Oh, if it's rational numbers, we have some, yes, some maybe we will subtract some numbers. But now when I will say my function is f of n, yeah, then we will think that n is counting numbers. Okay, 1, 2, 3, and so on, positive integers. And we not really, if we would like to talk about this function, we will think, okay, this is a sequence, and this will be the notation. Okay, a sub n. Okay, yeah, always the introduction to the chapter is a little bit more details and definition, concept, and labels. Okay, now that's the notation, a sub n, and we're not really saying like y, yes, y equals to a sub n. No, we will say a sub n, and we're using these curly brackets. Okay, that means that's a sub n, or to have more details, we will have the same thing, and here, yes, on the right-hand side below, we will like state the initial point. That's when we're starting with n1. We will usually start with n1, meaning that the first term is defined for n1, okay? And then it goes to the infinity, always goes to the infinity. If nothing is stated, we always start with 1. Sometimes we may, for instance, say, I would like to start the terms for like starting from n different than 1, like for instance, 3. That means what we will have. Okay, I will show maybe when we will have the formulas, because this one will be a little bit confused. Because what we, in order to define the sequence, the same like define the function, we will have a formula for the function, like for the sequence, for that pattern. Like for instance, x squared. Yeah? We know function, quadratic function x squared is parabola. And then when I substitute 1, I will square 1. When I substitute 2, I will square 2, and I can produce the outputs, the result. But we have the formula. That's my point. The same thing will happen for the sequence. We will have like a formula for this, but the formula will depend on n. And then but we always have to think n is never negative. In order to create like a term, we will substitute instead of n1, 2, 3, 4, or maybe, as I said, maybe we will skip a couple of terms, and we will say like we're starting actually from 3 or from 30, depends on the formula. Let's actually see. I have on the next slide. Okay, that's me. Yeah, sequences we will definitely have, and we kind of have 3 different like ways to but it's still this. It's a formula. That's mean I can use defining formula, like the explicit way to have to represent the sequence formula. Even like preceding notation is also the formula. You will see this. Or I can actually write out all of the terms. Not all of them, because it's infinitely many, but at least a couple of first terms. Yeah? I will call like expanded form. Let's see. I have 1, 2, 3, 4 examples. Okay, let's see. I just took an example, the formula of the sequence n over n plus 1. Okay, that means this, it's like a formula, or I can write like this, because this one is like a sub n equals to, that's the formula. But this notation, yeah, equivalent. Either way, you will write a sequence is good, or we can list a couple of terms. Can you tell me what is the first term of this sequence? Because I typed here, but I would like to see if you can give me. You may notice this is the formula. The first output, the first term will be defined for n equals to 1. Just substitute instead of n 1. Replace n with 1. That means what's the first term? Oh, come on, somebody. Yes, 1/2. The second term? Thank you, Deepan. 1/2. The second term? Substitute instead of n the second number, which we know we're going by counting numbers. 1, 2, 3, 4, 5, 6, 2/3. Thank you, Zander. Maybe one more. What's the third term? Yes. And then, yes, thank you. And then the pattern continues. And I type this. That means this is the A sub 1, this is A sub 2, A sub 3, A sub 4, and so on. This is A sub n. Yeah. Actually, since we're talking, how will be defined A sub n plus 1? This is A sub n. How we can define A sub n plus 1? Like how we can define the next term after A sub n? Yes, we will simply replace n with n plus 1. N plus 1 plus 1 plus 2. Yes, and we can add, yeah, that's perfect. All of the answers, thank you. Important, because we have to know what is A sub n and then the next term, maybe even one couple of extra terms, but using that n general terms. Okay, perfect. Now let's look at my second formula, n plus 1 over exponential form 3 to the n, and we see something like this, -1 to the n. That means this will be one additional thing that we don't really see in the functions. We don't have, because then it will be, could be a function, depends. But we don't really see that part. This is usually, that's the new. And what this -1 to the n, actually, what that component, that part of the formula does. -1 to the power of even numbers. What is -1 to the power of 2 or 4 or 6, 8? It will become +1. That means will completely, disappeared. What about, yes, thank you. What about -1 to the power of odd numbers? It will stay negative, right? -1 to the power of 3, 5, 7. That means when we see -1 to the n, we will have alternating terms. Assuming that the other part of the formula is positive. Right? But if we have this, this is like alternating, positive, negative, positive, negative. Okay, that's the same thing. You may notice but we have the equal, that's I'm calling formula, and then I can expand, have the expanded form. And we didn't really indicate, but when there's no indication, what we always starting from 1. Yeah, that means this is again A sub 1, A sub 2, and so on. And we may notice even terms are positive. Okay, another one, square root of n minus 3. And we can see we are kind of forced, yeah, to start from 3 because of the real outputs. Otherwise, we will have, I can't start with 1, because 1 minus 3 is -2. Negative numbers are not welcome under the square root. Okay? And then the first term will be defined for 3. And this is also interesting. That means please do not be confused. I know that we got 0 because I did substitute for n3, because that was the first allowed like number. We did get 1 because we did substitute for n4, and then we're going, yes, in order, 3, 4, 5. But even the first term was defined for n equal like 3. It is still the first term. That means I will still call a sub 1. That's what I was gonna say on the previous slide. Yeah, that's, you can see it's a little bit confused, but this is still first term. Yes, a sub 1, a sub 2, a sub 3, because this is an order. A sub 1 means the first term. We can see doesn't really mean that I did substitute n equals to 1 to get the term. Actually, no, based on the description, based on the instruction, I did substitute 3 because that I was told to do this for the first term. That means this is sometimes could be a little bit, yes, confused, that we will say, oh, it's a sub 1, the first term, and we're not substituting 1. Yes, we have to see what is the allowed, the first number. Yeah, that's we can see n equals to 3 to get the first term, but it's still called a sub 1. That's we may have the situation that they not really corresponds. Yeah? Usually they are, but we have to be careful. Okay, and then interesting example, trigonometric formula. We may have it, cosine of n pi over 6. And please notice, what is the first n value? 0. 0. Also, this has to be clearly identified if we would like to list the terms. 0 is not a counting number. 0 is not because we know when I count my students, for instance, in the classroom, I will not say 0, 1, 2, 3. No, but we adding that 0 occasionally because 0 is still interesting number. That's mean, and then the first term will be defined for n0. That's the formula. And then when I substitute 0 instead of n, cosine of 0, what is cosine of 0? Cosine of 0, it is 1. Yes, that's we can see it. This was defined for n0, but it's still a sub 1. Then if n is 1, what is cosine of pi over 6? Cosine of pi over 6. And then cosine of 2 pi over 6, which will be pi over 3. We can see that's this. Square root of 3 over 2, and so on. And that means this one is second term, a sub 2, but was defined for n1. Okay, I believe it's not difficult, but I saw sometimes the confusion. I will say, okay, what is the first term? And everybody's grabbing n1 and substituting. No, we have to always check. Always check. Yeah? If nothing is written, yes, n is 1, but not always. Okay, we good with this. Let's keep working. Oh, yes, doesn't mean that this has to start from 1. Okay, now I would like my students to help me with the pattern. Having an expanded form, we might need this skill, like we have to know. I can maybe change. This is the sequence. 1, -1, 1, -1, 1, -1. What will be the formula? Yes, we actually have this -1 to the n. I can maybe write like this. But now, shall I start with what n I have to put as a first value? Can we just say 1? 1 is not good. Yes, actually, J, yes, because -1 to the 1 will be negative. And we see that the first term is actually positive. That means I can say, I can say 0. Yeah, that's another thing, how we can change this. We may have -1 starting with 1, but yes, that's what I was gonna say, n-1 or n+1, starting from 1. This is 1. Yes, everybody agree? That means yes, all of these three are equivalent because the first term will be +1. -1 to the n, starting with 0, -1 to the n-1, starting with 1, and n+1, starting with 1, because we will get even number for the first, even exponent for the first step. Okay, good. Also, yeah, important how we can like change, manipulate a little bit with this, and yeah, respectively with the starting point. Okay, second formula. Even numbers, 2, 4, 6, 8. This is a sequence. And what is the general formula for the even numbers? Even numbers, using n. Oh, 2 times n, yes, 2 times n. And I think we have to start with 1. 2 times 1, 2 times 2, 2 times 3, 2 times 4, 5, 6, and so on. Because n is a counting numbers, 1, 2, 3, 4, 5, and so on. Okay, excellent. My next exercise, odd numbers. How we can define odd numbers? That's the sequence. Yes, we can say 2n+1, and I think we have to start with 1. Am I right? No, something is. How can I correct this? Because that's not right. 0, because 2 times 0 plus 1 will give us 1. What about if I would like to start with 1? Then how I can change the formula? Can I say -1? 2 minus 1 is 1, and then 4 minus 1 is 3. Okay, yeah, that's what we can see. That's the same thing. Both of them will give us the same sequence: 1, 3, 5, 7, and so on. I mean, that's how we can, yes, change a little bit the index and the formula. Okay, we know odd numbers, we know even numbers, we know alternating, and now I have just, it is better to change the formula or n values in this, either way, Zander, either way, because sometimes I want my students to be flexible and to change maybe the formula, maybe the index. Because what's happened, we may have the formula actually, that we will be not able to change the formula. And then we have to figure out what is the initial, like what is the starting point. Or we may be forced, I'm thinking about the next, next sections in the chapter, we may be forced to start, for instance, from like 1 or 2. Actually, what will be, when we starting from 2, let's say this, because we may have this question, how the formula will look like. Let's say the first term must be defined for n2. And we still need a1 to be the first term, this one to be the second term, third term. That means, please tell me what will be the formula if we will start from 2, because sometimes we have to do this later for the geometric sequence or series. It will be still 2n minus, please help me, please think, 2 times 2 will be 4, and we need 1. Then I have to subtract 3. I think so. Then the next number is 3. 2 times 3 is 6. Oh, no. Oh, yes. Yes, yeah, makes sense. 2 times 3 is 6. 6 minus 3 is 3. Then 2, 3, 4. 2 times 4 is 8. 8 minus 3 is 5. Yes, it works. Yeah? I think that's how we can please make sure that we understand this. Okay. Perfect. Let's keep working. This one is just for fun, but let's try to find the pattern. 3 over 5, 4 over 25, 5 over 125, 6 over 625, and so on. And we may also notice the alternation, positive, negative, positive, negative. Okay, that's what's the formula? We definitely have a fraction. We do have the alternation. Okay. But, okay, what we see, for instance, in the denominator, 5, 25, 125, 625, 3,125, maybe that's too big, but we may not, you probably notice the pattern. Okay, what's the pattern? What are the numbers in the denominator? Oh, Deepen has the entire formula. Let's see. I think they are power of 5s. 5 to the power of 1, 5 to the power of 2, 5 to the power of 3, 5 to the power of n, starting with 1. Yes. Then when we starting with 1, I think I have to add 1 to have even number, because negative 1 to the even number will give me positive, and the first term is positive. Okay, what we can put in the numerator, Deepen, you have in the numerator 2n plus 1. 2n plus 1 is an odd number. And I also see even numbers in the, just Colby is telling us 2 plus n. 1 plus 2 plus 1, 2 plus 2, yes, because we're starting with, we can say n plus 2, but it's, but it's the same thing. Of course, it's the same thing. N plus 2, 1 plus 2, 2 plus 2, 3 plus 2. Yes? Okay. We do have a formula. Everything, everything. I didn't see the even, oh, no. You good. Oh my, yes, you good. We have to, yes, we have to try. We have to make the mistakes. That's how we learn. That's how we learn even better and faster. It's okay. Okay. Oh, I typed my solution. Oh, I did put n minus 1. Do you see this? It's okay. It's also correct. Okay, let's keep working. Okay, now let's look at this one, because so far we have, like, I can even come back for a second. Yeah, like we had the formulas, like let's say 2n. Oh, we have another 2n plus 1. Oh, we had something like n plus 1. Yeah? We have the formulas, meaning that the formula of the sequence depends on n. Yes, depends on n. 2 times n, 2n plus 1, n over n plus 1. And we, let's say we're starting with like 1. That means what will be the 99th term? Oh, who knows 2 times 99? Yeah. What will be the 99th one? 198? Yes, 19. That will be the A99. Or for instance, what will be the 100th term for number 3? The 100th term, we can basically grab 100. Yes, it will be 100 over 101. And maybe 200. What will be the 200th term for this odd numbers? 401, am I right? Please just confirm. 2 times 200 plus 1, yes. That's even, that's odd, and that's some formula. That we can see how easy I can pick any like term, 1000th one, 2000th one, and we can get this because the formula depends on n, we're grabbing that n, assuming that the first one is defined for n equals to 1. And we can get not all of the patterns, and referring to the sequence, of course, can be defined this way. Yeah? We also have a way like to define a sequence. It's called recursive, like formula, recursive definition, meaning, and one of the famous recursive sequence is actually a Fibonacci sequence. Did you hear about the Fibonacci numbers? I'm sure you hear about the Fibonacci numbers. Yes, okay, let's see, because this is an example, but we may, I also have, we may create normal, like, yes, recursive sequence. Yeah, not that famous, but let's look at this one. And since this is like really famous, we're not really calling A sub n, we're calling F sub n, yeah, because Fibonacci. Fibonacci is the really famous mathematician, Italian mathematician, and he actually discovered these numbers, which the numbers are everywhere. Wherever you look, you see the numbers. Okay, I can show you. But what about the definition? A definition looks like this one. That means the recursive definition is the definition of the sequence not defined. The sequence is not defined in terms of n. It's actually defined in terms of the other terms in that sequence. So you can see that the nth term is defined as an addition, the sum, yes, of two preceding, like two terms in front of the f sub n, yeah? Because f sub n minus 1 is one before, and f sub n minus 2 is another one. And we just have to add two terms to create the third one. We have to add again two terms to create the next one. And also to start that procedure, we have to have at least the first two terms, and they are given. And that usually happens when we have a recursive definition. The formula depends on a couple of previous terms. We have to have these previous terms. That means the first term, let me write, the first term is 1. The second term is 1. We can see f sub 1 and sub 2 given. What will be the third term? Yeah, we can see we have to just, let me say this, f sub n. That means this will be the sequence, f sub 1, f sub 2, 3, 4, and then f sub n, n plus 1, n plus 2. That's what we did on the first slide. And f sub n plus 3, or before we have f sub n minus 1, f sub n minus 2, and so on. And you can see f sub n minus 2 is here. F sub n minus, minus 1, minus 2 is here. That's when we need these two terms, this one and this one. You can see they are there. We have to add them together to create the next one. Okay, that means if we have 1 and 1, what's the next term? We have to add them together. Yeah, that's how we read this definition. Okay, you have to help me because it will be a couple of addition. 1 plus 1? Where are my students? Use that hour. Help you, yes, thank you. It's 2. Now, what is the next term? Thank you, Kiran. Then again, we're taking the last two terms, adding them together to create the next one. What will be the next one? Yes, 1 plus 2, 3. The next one? Thank you, Zander. 2 plus 3, 5. Next one? 3 plus 5, 8. Next one? Couple more. You will be happy. Yes, yes. Well, okay, 13 plus 8, 21. 13 plus 21. Oh, 34, and maybe one more. I don't even have enough. 21 plus 34, 55, and so on. Okay, yes. That means I was just testing if you can read this definition and then you can produce the numbers. Yeah? That's we can see 2 terms and produce the next one. Adding the last 2 terms and it will be the next one. Okay. And now when we just, it's always like this, right? I'm like, we're discussing some theoretical parts, some definition, then we have the numbers. We will think they are just random numbers, but they look like a random numbers, 1, 1, 2, 3, 5, 8, 13, 21, but they are extremely beautiful, golden numbers. We can see them everywhere, everywhere. Everything which is like nice, and when you look at some shapes, some sizes, and if everything looks perfect, they definitely in some way they satisfying this sequence. Okay, if something is like something is not right, like let's say maybe the building or maybe even the car, when they developing some shapes and something seems to be maybe too long or too short, or maybe like, I don't know, too wide, too high, then probably it doesn't really fit to this pattern. Like that's the buildings, yes, or even human body will have this, this sequence of numbers somewhere. Art, music, everything in the nature, like lots of like trees or veggies, or they growing, or the shape, sizes of the of some animals. Everybody respect these numbers. Oh, programming, I'm not even saying we're using this a lot. Okay, so now I have a couple of funny pictures. Let's just spend maybe 2-3 minutes for fun. Oh, for instance, the tree. When you look closely how the branches are like expanding, they create a Fibonacci sequence. Always is like the first branch, and then it's 2, and then one of them will stay, not like it will not spread, it will not be divided, but one of them will be divided, and see 1, 2, 3 branches, and then again 2 of them will expand, one of them will stay, it will be 5 branches, and so on. And you can see 1, 2, 3, 5, 8, 13, 21. You may notice even after the session, you can go for a walk and you can look at this. Maybe not all of them, because we have so many mutations in these days, but I'm sure you will definitely find this. Okay, another, this was actually my drawing before I found this on probably somewhere on the internet. Okay, maybe this one is crazy, but I'm sure if we will look closer, we will find the Fibonacci numbers. Some piano keys. We have like 1 octave, then we have 2, 3 numbers in each set of like a black notes, 5 number of the black notes, 8 numbers of white notes, total numbers of notes, 13. Look at this. Otherwise, we'll be like, we will not get this beautiful tunes. Okay, some nature. If we will look at sunflowers or pineapples, this one is not easy to figure out, but it's also like, I think we have to look from the top, and then we will see how they expand. It's like 3, 5, 8, 13 of these, like, these. They are not hexagons, pentagons. Okay, the proportion in like human face, the entire body. We will, for instance, this is a good picture. We will have like the length of our from one bone to another, like 2 units, 3 units, 5, 8. Because then Okay. Oh, okay. And then this is like a golden ratio. Like for instance, if we will be, I mean, we can even do the experiment now. If I will ask you to take a pencil and paper and draw a rectangle really quickly, like draw the rectangle. Yeah, like you can even try later. Draw a rectangle without thinking. Okay, now when you will measure the length, like everybody, you can measure the length, you can measure the width and divide length by width. Everybody will get the number on the calculator if you will measure again the length of your rectangle, the width, and divide length by width. You will get the number around 1.6, 1.7, maybe 1.8, but 1.6, 18 is the perfect. Everybody will get this. Yeah, that's how we are connected. Scary. Yes, Jay, spin. Okay, but and this number is called golden ratio. And that's the golden ratio. As you can see, A over B. Because what's happened? Because nobody will, when you will draw a rectangle, you will do something like this, right? You will not do like this. Yeah, you will not even draw a square. No. You will draw a perfect rectangle because you know what rectangle is, how beautiful a rectangle looks like. Yeah, like a, yeah. And rectangle is a rectangle. It's the most beautiful shape. Yeah. When you look again around you, we always have rectangles. For instance, like windows. I mean, sometimes we may have some circles, some fancy, but windows are usually rectangles. They are not square. Square is not, okay. But what we can do in this perfect shape to get this golden ratio, when you look at these, like, yeah, you can see I can start from the square 1 by 1, and then I can keep adding like 3 by 3, 5 by 5, 8 by 8. Then, yes, and then because adding another like, because we adding 8 plus 5 to get 13, and then 13 plus 5. No, I need wrong. I need 8. Okay, that's 13. Where is 8? Oh, hang on. No, it's definitely here. I'm just saying wrong. 1 by 1. Okay, this is 3 by 3. This is 8 by 8, 13 by 13. This will be, what is that? This is 8. Okay. Yeah, this is 8, 5 and 3. Because this is 8. 8, 13, 21, and so on. Okay. For some reason I just missed that. Yes, missed that 8. You can see we just creating this, these rectangles. Beautiful, each of them has golden proportion. Also, when we will take the neighbors of the Fibonacci sequence numbers and we will divide, we will also get this golden proportion: 3 over 2, 5 over 3, 8 over 5, 13 over 8. That's the same. That's from the rectangles. It's that golden proportion. Yeah, that's me. And again, if we have this Fibonacci numbers and golden proportion, everything is like beautiful. It's supposed to be. If something is a little bit like off, then it's still okay. It's still okay, but we always tend to create this. Even when we look at some painting, I don't have this example. I have to, because when we look at the painting, usually the artist is trying to put the main, like maybe house or maybe people, whatever the painting is about, not on the center. Yes, always like on one side, and then is everything. Then it's that's what I realize. I have to get some example. Okay, and then I have another like couple of Mona Lisa, some other, and this golden ratio we call like a is irrational number. We call phi or phi, I will say, respecting the Greek, and it's that number. Always, all of the in the architecture, in painting, they definitely using this ratio. Okay, what else? This one is actually different. This one is like, I mean, still golden proportion. It's a face. It has to respect the golden ratio. And then, yes, I like the ear, egg, music notes, or some tornado. Yeah. Okay, lots of things. I don't know if this is true. I don't know. But yeah, I found this one. Oh, this is a beautiful painting. And this was my drawing. I didn't find this on I mean, you can find, we probably know Pascal triangle, yeah, like how we create. And then when I start adding them this way, 1, 1, and then 1 + 1, 2, 1 + 2, 3, 1 + 3 + 1, 5. And then, yes, I don't have the entire 1, 4, and 3, 8. And you can see these numbers, Fibonacci sequence. Yeah? Everywhere is a Fibonacci sequence. Okay. Oh, I think we spent more than 5 minutes. Okay, but this is here. Please remember about the Fibonacci numbers. Please maybe think about this golden ratio. Beautiful shape, square, rectangle. And definitely we have to know how to read the recursive definition. Yeah, Fibonacci is a perfect example. Now I have a quick example for recursive definition, and I just want to check if we good reading this definition. I want the first 3 terms. That means what is A sub 1, what is A sub 2, and what is A sub 3. No more magic. Okay, A sub 1 is given. Now let's see how the definition is provided. The next term, n plus 1, yes, A sub n plus 1, is defined as a 1/2 A sub n plus 2. Yeah, that means, for instance, A sub 2 will be defined as a 1/2, and we can see this is n plus 1, and this is 1 term less, 1 term like before. If this is 2, this will be 1. Okay, and we know what is 1, 3. 3 plus 2, 5/2. Okay, and what about the third one? 1/2. What will be this term? A sub, what index shall I put here? If this is 3, then this one, based on the definition, it's 1 less, 2. Thank you. That's what I wanted. Okay, and the second term is this one. Okay, who can do the arithmetic? 9/4, please check. 4/2, 9, 5 plus 4, 9, 9/2 times 1/2, 9/4. Okay, I hope I didn't make the mistake. And then we can keep working. Thank you. The only disadvantage of this is, yes, because do you think you can tell me right away what is the 10th? For instance, 10, A sub 10? Because we can see we do not have the formula. What we will need to get A sub 10? We will need A sub 9. Yes, we will need the 9th term. In order to get A sub 9, we have to get A sub 8. Yes, that's sometimes is the disadvantage, but if we need, we can still do it. Or we can ask the computer to do it if we know what we're asking for. But this is the disadvantage. But sometimes, as I said, the pattern is so complicated that we cannot have the explicit formula in terms of n. Okay, that means you know that something like this exists. Okay, let's see. We still have a couple of things. Okay, because what is important, everything is important, what I said, but what is the point of this, the sequence? We have to know, we have to identify how sequence behaves. Okay, that means, for instance, this sequence n/n plus 1. We have expanded form, 1/2, 2/3, 3/4, 4/5. And now the question is, if we will keep like listing the terms, like we would like to investigate the behavior of this sequence at infinity. Yes, at positive infinity, of course, because we're not looking at negative numbers. At like how the terms are behaves. Are they getting like bigger and bigger? Are they getting like they expanding without any bounds? Basically, what I'm saying, we have to find a limit at infinity of this formula. Right? That's the main thing. In order to do this, we will adopt all of the limits property. We will do exactly the same like we are doing for the function. Actually, what is the limit? What do you think? Where these numbers are going? 1/2, 2/3, 3/4, 4/5, 5/6, 6/7, 7/8. Or you can think about this formula. What is the limit at infinity? Limit, and now I will put n. Yes, it is 1. Or actually, let's pretend that we still don't know because we theoretically don't know. I can even mimic that this is a function, because even if we're talking about the dots like a discrete, they still follow the same like path, the pattern like function. And this limit at infinity is 1. Yes, these terms are they approaching 1. They're getting bigger and bigger, but they will be never greater than 1. And this is the point. Okay, we have to figure out if the sequence converges to a finite number, if the limit exists at infinity as a finite number, or if the sequence is like the terms of the sequence expanding without a bound, we will say divergent. Yeah? The same terminology like from improper integrals. Okay, but what we can do, we may plot the points. Oh, I'm just writing that we may use just the number line, the first term, the second term, the third, but that's one dimension. No, let's focus on the 2 dimensions. We will adopt the Cartesian plane, and the x-axis will be that's the input. Will be represented actually by n, 1, 2, 3, 4, 5, and the y-axis is the output, is the function, is the sequence a sub n. That means the first term is 1/2. The second term is, what is the second term? 2/3, and so on. Yes, 3/4, 4/5, 5/6, and you can see all of these dots are the dots represents the terms of the sequence. When I actually put it x plus, I can use maybe different color, x over x plus 1, that means this is function. And when we will start from 1, function will behave like this. But function is we have continuity. Yes, for the sequence, we're only talking about the dots, discrete mathematics, but we can see the behavior is the same. Yeah? They behave in the same manner. That means that's what we can do. We can plot the graph, and using the graph, we can plot the terms of the sequence, and we will find the limits. Okay, that means graph and the limits. This sequence is, and we can say converges to 1. Okay. And see how easy it is. And I just write this, we will compute a limit, and if the limit exists, we will call convergent, otherwise is divergent. If the limit does not exist as a finite number or is infinity, it's just divergent. Yeah? In order to say that the sequence converges to a finite number, we have to have that one finite number as a limit. And again, the limits we will compute exactly the same like we did in Calc 1 or in section 4.5, because we will probably have lots of indeterminate forms. We will see. Okay. Yeah, that's for instance here. I draw it. The green part is like a function, but the dots are the sequence. We may compare them, that they are the same. That's the reason that we adopt all of the properties from the from functions, the limits law. This one is a little bit crazy, but it's also, yeah, looks nice. And the limit is L, the limit is L. I can even write limit of A sub n is L. These dots are A sub n, okay, at infinity, in both cases. Okay. Okay, that's what I just said. Sometimes we may rewrite, that's what I did. We may just take exactly the same formula and rewrite in terms of X. Then we will maybe see better. Yeah, that's what I did. And I asked you what is the limit, and I just replaced N with X, but it's exactly the same thing. Just to know that when we have X, it's a nice continuous curve. When we have N sequence, they are just the dots, the terms of the sequence. Okay, and we can compute that limit. And oh yeah, that's the same thing. If the terms are going to the infinity, then the sequence is divergent. Okay, and then we are adopting all of the properties. I mean the limits law for the sequences: addition, subtraction, constant, multiplication, division, powers, all of the laws. I don't even have to list them. You probably are using them without even thinking that we're using them. Okay, and then squeeze theorem, for instance, we may use. We also remember. And what else? Okay, this one will be another like property, it's a theorem that we will use a lot. And we didn't really have this for the function. That's in, for instance, if I will give you 1 over n, the sequence 1 over n, how these terms behaves. Is this sequence 1 over n convergent or divergent? That's the main question. Sequence 1 over n. You may think right away, we have to check the limit at infinity. What's the limit of 1 over n? Or we may think 1 over x. What is the limit? Oh, 1 over big number. I can list this 1, 1/2, 1/3, 1/4, 1/5. We know where this goes. 1 over big number goes to 0. That means this is this sequence is convergent. Yes, convergent to 0. And I can even, I can draw this. This will be A sub n, and first, second, third, fourth, fifth. And the first term is 1. This 1, 2, 3, 4, 5, 6, 7. The second term is 1/2. 1/3, 1/4, 1/5. I mean, when I will think about the function will go like this. Yes. 1/4, 1/5, 1/6, 1/7, 1/8. Definitely they're approaching 0. They're getting smaller and smaller. They will be never negative, but almost, yeah. That means the limit is 0, convergent to 0. Okay, but now, what about this one? -1 to the n times 1 over n. How this sequence behaves. Please tell me the terms. Actually, let me add a slide. I know that it will be just 5 more minutes, okay? And then I will finish everything what I was planning to do. You still have a couple of additional videos, yes? You saw them. Okay, what about this one? -1 to the n times 1 over n. What is the first term? Maybe we can see just this, but I can use that theorem because that's -1 is the first term, then +1/2, -1/3, +1/4, -1/5, and so on. We don't need that positive. Okay, when we will plot this, okay, first, second, and so on. Okay, that's me how the terms behaves. Are they approaching one finite number? or they oscillating? Oh, negative one. That means the first term is -1. The second term is 1/2. The third term is -1/3, +1/4, -1/5, +1/6. That means when I will take, what do you think? It's a little, yes. That means this is also extremely easy, but could be extremely confusing. Definitely the terms are like oscillating. But what happened when I remove that negative for a second, this alternating part, and I will look only at this main like magnitude. The magnitude is getting smaller and smaller, 1, 1/2, 1/3, 1/4. Yeah? And that means doesn't matter if they oscillate, because they jumping above and below the x-axis, but they approaching, yes, it's like kind of like a snake is getting lower and lower and lower. That means, yes, the limit is 0 of this, is approaching 0, converges to 0. That means this entire sequence converges to 0. And I hope we can all see this. If the magnitude will be bigger and bigger, then even if that's like no, because one that on the positive part, it will go above to the infinity or below to the negative infinity. But this magnitude is getting smaller and smaller. That's mean now, if like properly, explicitly, how we can compute that limit, because you will take the limit at infinity, put the formula, and look at this limit to find if the sequence is convergent or divergent. If we see this alternation, it is really helpful to take the absolute value, okay? And let's see how absolute value is changing this. -1 to the n sometimes is -1, sometimes is +1. Absolute value always makes positive. That means this will be positive. 1/n is positive, it will stay positive. That means basically that's how absolute value affects the formula, just removing this alternation, this negative. Okay, and this limit, 1 over big number, is a small number, 0. That means now, if having alternating sequence and investigating the behavior at infinity, we will apply absolute value. And if the new formula of the formula of the absolute value is the limit is 0, then the original alternating sequence is also 0. Then this implies that this limit is also 0. Okay, but this has to be 0. The absolute value of the sequence, the limit of absolute value, must give us 0. Then the original one is also 0. And we can see because of that, yes, that snake. If that absolute value, I can actually, yes, I can give you an example in a minute, is different than 0, then we have small problem. But if the limit of the absolute value is 0, then the original sequence is also convergent to 0. Let me come back to the previous slide. That's what I am, yes, talking about. If the limit, yes, of absolute value is 0, then the original sequence has also limit at infinity 0, but only 0, right? And then we can say it's convergent to 0. And this is usually that nice snake, lower and lower behavior. For instance, I don't know if I have this, but let me add, probably I have it somewhere. What about this one? A sub n equals to -1 n over n plus 1. We did the first one. How this sequence behaves? We may think about the expanded form. That means the first term is 1/2, actually negative, right? The second term is 2/3 positive. They will alternate. And then 3/4, 4/5, 5/6, 6/7. Let me put positive, negative, and so on. Okay, that means now we can plot Yes, or we may use the property right away, but let's do the longer way. That's actually n. A sub n. Okay, first, second, that's the terms. Yes, 3, 4, 5, 6, 7, 8, 9, and so on. Okay, the first term is -1/2. Okay. The second term is positive 2/3, a little bit more, and then negative 3/4, positive 4/5, negative the fifth one, negative 5/6. We know -1. Yeah? Because they will go, every other term will go closer and closer to 1. I mean, when I will try maybe to like combine them, like drawing this function, are these terms approaching one finite number? Because what they're doing, they're oscillating, but the magnitude is not getting, it's not getting smaller and smaller, the distance from above and below, from n, from x-axis. Okay, that's me now. The proper way is to take this formula, -1 to the n plus 1, that's the sequence, and we're trying to find the limit at infinity. That's how we can figure out if the sequence is convergent. Okay, what we see? Alternation. Let's apply the absolute value. -1 to the n is gone. This is positive. This will stay. What is this limit at infinity? n/n plus 1, x/x plus 1. You may picture, you can imagine this. Oh, the same degree, the same function. Yes, thank you, Noah. 1, it's 1. Okay, that means this limit is 1. It's not 0, like the theorem was then. If this limit is 1, then we may conclude that this limit actually does not exist as a finite number, because this part is 1. Yeah, how we can think, but this is only, of course, this limit is 1, and that part is giving us positive and -1. I mean, positive, negative, alternation. That means at the very, very end, the terms we may notice, +1, almost, +1, -1, +1, -1, +1, it will like oscillate between two numbers. Yeah, that means this is kind of like an answer, but it's not one finite number. Yes, that means the sequence does not, the limit of the sequence does not exist. Sequence is divergent. Divergent, okay? We can say, that means if the limit is 0 of the alternating one, then it's getting smaller and smaller, then it's convergent to 0. But if it's different than 0, then that number 1, we have to think, okay, it's 1, but with the alternation, it's positive, negative, positive, negative. Yes, D and E, or I mean, yes, it's the same thing. If the limit does not exist, the sequence doesn't really go towards one finite number, we will call divergent. Yes, Gabriel, we can say it's the same thing. Okay, good. Oh, okay. Let me just check. Okay, where am I? Okay, we actually investigated this one just yet, and then what we have to do, we have to just find a limit and limit and limit. You can definitely get this. Let's maybe do 1 or 2 examples. It will be extremely easy. Okay, what about sequence like this? ln of n over n. You can probably tell me right away what is the limit at infinity of this behavior, of this like formula. Yes, we know that it's infinity over infinity, and it's just an important message. But we also know the relative rates of growth. Yeah? Which function grows faster, natural n or n? We know that this one, if the denominator is winning, the limit is 0. But just in case, if you will say, oh, it's indeterminate form, and I really would like to use the L'Hopital rule, we may use it. We may use it. But what is, I know probably sounds silly, but we have to rewrite the same formula if you decided to use the L'Hopital rule in terms of x. Okay, and now let's see. Infinity over infinity, derivative of ln of x is 1 over x, derivative of x is 1. When I rewrite this, is 1 over x, 1 over big is small. Of course, we knew it. But do you possibly know why most of the mathematicians are a little bit crazy? Like they don't like seeing n and applying the L'Hopital rule, which is the same rule. Yes, you will think why we have to do it. What I did, how I got 1 over x. Yes, what I did. Yes, thank you, Deepan. I took the derivative. And when we see n and have the sequence, we only have like, oh, my pen behaves really weird. We only have like a dot, 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 dot. When we see x, we have a nice and continuous function. Do you think we can get the derivative of something that is not continuous? Do we remember, like in order for the function to be differentiable, we have to have continuity. If we do not have, yes, when we do not have continuity, we just have, yeah, then we will be not allowed to take the derivative. And still the rules, the tools apply, it's correct. But it's just, yeah, it's just more appropriate mathematically, like we're respecting all of the very, very fundamental rules of calculus when we rewrite in terms of x. Okay, that's mean, please just remember, if you will decide to use the L'Hopital rule, just grab the formula, rewrite in terms of x and apply the rule. But probably you will always use the relative rates of growth and you will not use the L'Hopital rule. Maybe, we don't know, maybe for more complex. But when it's infinity over infinity, always think which function grows faster, and that's the terms. Okay, what we have? What about this one? Negative 1 to the n. Is this sequence convergent or divergent? Negative 1, positive 1, negative 1, positive 1, negative 1, positive 1. What about the terms? Are they going in one direction? Negative 1, positive 1, negative 1, positive 1. No, they just oscillating. That's why the limit does not exist. Yeah, it's the sequence is divergent. It's just jumping, yeah, from one value to another, one value to another. We need one point, one like direction. That's one unique value. This is definitely divergent. Okay, what else I have? Oh, we know this one. Does this limit exist as a finite number? Or is this sequence convergent? Negative 1 to the n over n. What is this limit? When we apply absolute value, it's only 1 over n. 1 over big number is 0. If it's 0, the original one is also 0. Yeah, it's the same formula that we did that snake. Okay, I know. Let me check. I think I'm almost done. Okay, this one. What about this one? What about this limit? Sine square of n over 3 to the n. Which term grows faster? We can still kind of apply the relative rates of growth. Or we may use the squeeze theorem. Sine of n. What are the values of sine of n? When we squaring also, maybe sine square. No? Okay, let's try. Sine of n is definitely between -1 and 1. When I square this, yes, it's definitely positive values, and 1 square is still 1. And now when we divide by 3 to the n, right? That means this goes to 0 anyway, because it's 0. 3 to the n is a big number. Yes, that means 1 over big number, small number. Then this one is also 0. This sequence converges to 0. Converges to 0. Okay, the terms are getting closer and closer to 0. We may think that, okay, sine of n is the maximum value is like 1. Yes, and this is infinity. I mean, this is informal. This is really informal, but 1 over big number is a small number. Okay? But we have the nice squeeze theorem. Okay. Also, for instance, something like this, sine of pi over n. Yeah, we have the inner function. That means in order to find this limit, you probably know sine of pi over n. We will, sine is continuous. We will just focus on the same property we have for the function. We will focus on the inner function, and the outer value will stay. We will apply. Okay, what is pi over n? Pi over big number? 0. Sine of 0? 0. Converges to 0. That's when we can see this section is mainly about computing a limits with indeterminate forms, possibly, maybe not, and with some alternating like forms. That's maybe a little bit new, but it's just the limits. Yeah, that's when practice the limits. Okay, before we leave, one more. Okay, this one. Let's do this one and this one. 2 more. Okay. I'm just asking evaluate the limit, but I can also say, please determine whether the sequence is convergent or divergent. The same thing, the same thing. Okay, cosine of n pi, because that's interesting. That's actually really interesting. Let's put a star. Cosine of n pi. Important, because I will refer this for the entire chapter 10. Okay, let's actually see cosine of n pi, how this behaves. Cosine of 1 pi, cosine of 2 pi, cosine of 3 pi, 4 pi, and so on. What is cosine of 1 pi? Negative 1. Cosine of 2 pi? Positive 1. Cosine of 3 pi? Negative 1. Positive 1. That means it's really interesting, because cosine of n pi, only cosine of n pi, yes, behaves exactly the same like alternation, negative 1 to the n. And sometimes we replace this, because when we see cosine of n pi, it's a little bit, yes, a little bit weird. But cosine of n pi behaves exactly the same like alternation, negative 1 to the n. And we know that this limit does not exist as a one finite number. Yes, it's flips between, that means the limit does not exist, just oscillate between negative 1 and 1. The sequence is divergent. Divergent. Okay, good. And one more, extremely easy. Who is first to give me the answer? How this sequence behaves? E to the 1 over n. Yeah? What about the limit? Oh, too fast. Oh, I'm changing this. Limit of, actually, because, yes, thank you. I think it is 1, because we have to just say e to the power of 1 over n. 1 over big number is small number, yes? This sequence converges to 1. We don't have to, but we can e to the power of 1, e to the power of 1/2, e to the power of 1/3, yeah, like the 4th root, the 3rd root, 4th root, and so on. And then e to the power of, yes, 0. 1. That means all of the terms, they will be almost 1. Yes, almost 1. This sequence converges to 1. Yeah, it's extremely important that you will practice, and then I can create lots of formulas, but you know, that's mean, please practice all of the, like solve all of your homework, yes, questions, but any sequence, and try to find the limit, because it will be so important to know if the sequence is convergent or divergent, and if it is convergent, converges to what number. Yeah? It will be easier for the rest of the all of your math classes. Okay, that's enough. I think I can finish the session now. I'm really sorry that was so long, but sequences are so nice, so nice. I can even solve for the rest of the afternoon and the evening. Please check the additional videos with like small portion of still of this section. And yes, enjoy your sequences, and especially the Fibonacci one. Go and explore around. Thank you. See you next week.